Hi there! I just came back from a holiday involving lots of hiking and I took these two power banks with me. Both claim a capacity of 10,000 milliamp hours, although during the trip I found one ran noticeably longer. So now that I'm back in the lab, I thought it would be a good idea for a quick review and run some tests. These power banks are still in use by the family, so I'm not going to take them apart for now. But let's see what facts we can determine just from the outside. The first one is the Energizer UE10007, a chunky block with a black rubberized surface and blue end caps. The box shows the key specs: capacity 10,000 milliamp hours and an energy content of 37 watt hours maximum. This of course means that the 10,000 milliamp hours are based on the average lithium battery voltage of 3.7 volts, and the usable capacity at the 5 volt output will be significantly less. It charges at 5 volts 2 amps over micro USB and has an output rating of 5 volts 2.1 amp. It does not say how that applies to one or both outputs. The weight is stated as 240 plus minus 24 grams, and I wonder why that huge uncertainty of plus minus 10%. The only thing I can think of is that they may put in cells from different manufacturers. My unit weighs 239 grams and I paid 23 pounds for that in a local shop. I know, way too much, but I was in a hurry and I needed this power bank for a next day trip. The small piece of paper that came with it can hardly be called a manual. It basically repeats the specs from the box in several languages, while the reverse gives basic how to connect information and explains what the 4 charge status LEDs mean. Nothing special here. The second one is from Xiaomi. There are many Xiaomi power banks out there and many of them are fake. This one came from an eBay seller, Sky City 19, for around 15 pounds and appears to be genuine. The unit is in a sleek metal enclosure. The box came with one of those security seals and it did check out on the Xiaomi website. The manual in the box is completely in Chinese, but thanks to the internet, an English manual is easy to find and download. The capacity is again 10,000 milliamp hours and 37 watt hours energy. I like that they specify 2 capacities: the 10,000 milliamp hours for the lithium battery at a nominal voltage of 3.7 volts and the actual usable 6,500 milliamp hours available at the 5.1 volt output. This is an old bugbear of mine and I have made a video explaining why these 2 capacities are necessarily different, so hats off to Xiaomi for giving both values. The Energizer is of course silent on that matter. Other difference to the Energizer are that the Xiaomi can charge fast using 9 volts if the power supply supports it, and it can produce 5, 9 or 12 volts outputs as well. Not stated is the weight, which is 251 grams for my model, so 12 grams heavier than the Energizer. Charging the Energizer from empty using a Samsung power adapter that can provide 5 volts 2 amps or 9 volts 1.67 amps. I'm using the Ruideng UM34C USB tester to keep track of the charge going into the power bank. In case you're interested, I've put a link to my review and teardown of this USB tester in the description below. Charging takes several hours of not much happening, so let's cut right to the end. So at 4 hours and 46 minutes the charge current drops to 0. It's a bit hard to read, but we have pumped in 8,400 milliamp hours or 43.276 watt hours into the Energizer power bank. Let's do the same for the Xiaomi, which is also completely discharged. The setup is the same as before. It is interesting that the Xiaomi does not shift to the fast charge mode promised in the manual. It stays at 5 volts for the whole process. Initially I thought it might be because the Samsung power adapter I'm using only offers 9 volts at 1.67 amps instead of the 9 volts 2 amps stated in the Xiaomi manual, but I tested it with a Motorola power adapter which offers 9 volts 2 amps, but the Xiaomi was not impressed and stayed at 5 volts. Around 5 hours and 20 minutes later, the charge current drops to 40 milliamps and it stays that way. Probably some form of trickle charge or just to drive the charge indicator LEDs. We have put in 9152 milliamp hours or 47.201 watt hours. That is about 9% more than went into the Energizer. I decided to investigate the problem of the missing fast charge of the Xiaomi further, and it turned out that both the power adapter and the USB cable were the problem. The cheap cable I used happened to have only 2 wires for power and no data connection. When I changed this to this 4-wire flat cable and the Motorola adapter, the Xiaomi switches to 9 volts charging without problems. It starts at about 1.8 amps, but I discovered that the current ramps up later to the full 2 amps with the Motorola adapter getting worryingly hot in the process, while the Xiaomi, thanks to its large metal case, just feels slightly warm. Just for the record, I did also try using this cable and power adapter on the Energizer, but it always stays at 5 volts. Fast charging doesn't work with the same cable but the Samsung power adapter, even though that adapter can fast charge my phone with 9 volts at 1.5 amps. As these two adapters are the only ones I have that can do fast charge, I don't know if there's a compatibility issue, but my guess is that the Xiaomi simply asks for 9 volts 2 amps, and since the Samsung adapter can only deliver 9 volts at 1.6 amps, fast charge is never started. For discharging, I'm using my electronic load, the build of which is in another video I link below. It is set up in 4-wire mode, so the extra sense input compensates for the voltage drop across the wire from the battery to the load. The load is set to constant 2 amps. The Energizer is first. Discharging takes again several hours, and apart from the slowly reducing charge indicator LEDs, nothing much is happening. The output voltage of the Energizer is not great, only 4.89 volts. This means connected phones or tablets will charge a little slower. Finally, 3 hours later, we reach the point where the Energizer power bank shuts down. In total, we extracted 6039 milliamp hours or 29.53 watt hours. Let's try the same with the Xiaomi. The setup is identical, including the discharge current of 2 amps. It is immediately obvious that the voltage of the Xiaomi at the same load is slightly above 5 volts, much better than the 4.89 of the Energizer. About 3 hours and 15 minutes later, the Xiaomi power bank shuts down too. In total we extracted 6591 milliamp hours or 33.18 watt hours. Here are the discharge results, which by the way confirm what I experienced when using these power banks during my travels. The Xiaomi has a bit more capacity, and because it maintains its voltage slightly above 5 volts compared to the disappointingly below 4.9 volts of the Energizer, charging your phone goes a bit quicker too. The Xiaomi matches its stated capacity of 6500 milliamp hours at 5 volts, but neither power bank did deliver 37,000 milliwatt hours based on 10,000 milliamp hours times 3.7 volts with this discharge current because of the losses in the boost converters. Indeed, from an efficiency point of view, both are not great. In generally, on all power banks, you put more energy into it than you can back out. For the 2 amp discharge, you already saw, the efficiency is slightly above 70% for the Xiaomi and around 68% for the Energizer. At lower currents, It's a neck-and-neck race with the Energizer leading at 1 amp and the Xiaomi at 0.5 amps. But we are still just getting at best 75% or 3/4 of the energy back that we put in. This is a bit disappointing because from other smaller power banks I tested earlier, I would have expected higher values of 80% or even 90%. For this test, I want to check the response to increasing load and overload conditions. I'm using my PowerMon device for recording the behavior. There's a whole series of videos in my channel about designing and building this tool, links again below. Once the recording is started, I'm increasing the load current in 200 milliamp steps. There is a small voltage difference between the display on the PowerMon and the electronic load because of the drop across the 0.1 ohm shunt resistor in the PowerMon. Similar, with increasing current, there is a noticeable voltage drop across the wires from the power bank. I measured the resistance of the wires to be 70 milliohms, which allows me to correct the readings later. At full load of 2.1 amps and above, the Energizer is still going, but its voltage is sagging ever more. Okay, at 2.9 amps, the Energizer's protection circuit activates and turns the output off. Now, both power banks have two outputs, so it makes sense to check how they behave if both are loaded. Unfortunately, I only have one electronic load. Therefore, I'm going to use this light with a USB tester as a second load. Unfortunately, its current is of course somewhat voltage dependent. It draws around 380 milliamps at 5 volts, which isn't that much, but it should allow us to see if it makes any difference. I'm running the same test as before, but now with the extra load of around 380 milliamps. The light is just out of view to avoid totally swamping the camera. It is interesting to note that the voltage at the highly loaded output is dropping, while the voltage at the output driving the light is almost unaffected until close to the end. Which happens at 2.6 amps this time compared to 2.9 before with only one output. This makes sense because the difference of 300 milliamps is about the extra current we were drawing from the second output. Repeating the same test with the Xiaomi, first with one output. It is interesting to note that the output voltage actually increases slightly when a moderate load of 0.6 amps is applied. But at ever higher currents, the measured output voltage decreases as expected, partly of course because of the voltage drop in the wires. At 3.0 amps, the Xiaomi had enough and turns the output off. Repeating the same test with the second output loaded with a USB light via the USB tester. Notice how the voltage on the second output increased again after the electronic load added 200 milliamps to the total. As with the Energizer, the second output voltage remains quite constant despite the increasing load on the first output. As expected, the power bank turns off when the combined current from the electronic load and the additional light exceeds about 3 amps. This matches the spec, which states that the maximum load is 15 watts from both outputs. Here are the output volts over load current plots from the 4 load tests. Energizer on the left and Xiaomi on the right. We can see that in all cases the output voltage slowly drops as the current increases. Also, the Xiaomi has this slight bump where its boost converter suddenly increases the voltage slightly, possibly because it is switching to a different mode. Noticeably in all cases is that the Energizer produces a lower output voltage and turns off at a lower overall current. To see how the Energizer handles a phone that is capable of fast charge, I connected a Samsung A40 to it. As expected, it can't support this and charges at slightly below 5 volts at 1.2 amps, resulting in 6.25 watt-hours of energy transfer from the power bank to the phone. The same test with the Xiaomi, which should support fast charge. It starts at 5 volts and then immediately switches to slightly below 9 volts at 1.5 amps, which is 13.26 watt-hours of energy transfer, double that of the Energizer. To see if it can provide the promised 12 volt output as well, I connected a USB trigger tester in between the UMC34C and the power bank. All this little device does is to send a quick charge 2.0 or 3.0 command to select 5, 9 or 12 volt depending on the selector switch. As you can see, the Xiaomi supports all three settings. Off camera, I ran a simple discharge test at 12 volts, but when I came back just before the test ended, it appeared that the Xiaomi has switched to 9 volts all by itself. To find out more, I repeated the test, but as you can see, this time I recorded the behavior using my PowerMon tester. And since I have the PowerMon running anyway, I decided to record the behavior at different currents at the same time, but then let it discharge at the Xiaomi's stated maximum of 1.2 amps for 12 volts. And sure enough, about halfway in the discharge, something strange is going on. The voltage is jumping up and down like crazy. After about 2.5 hours, the power bank cuts off with a total of 32.71 watt-hours energy delivered. Here's the plot of the total discharge. The efficiency for 12 volt 1.2 amps is not great at just 68%. Immediately obvious is this weird behavior in the middle. I tried to zoom into this, but static graphing is just not up to that, so I used the same little interactive Python graphing utility I wrote for my video about an Ansman battery charger. I saved the sequence of views of the data earlier, and by just cycling through them, you can see first the zooming into the crazy jumping up and down region, revealing more and more details, and then as I progressively scroll to the right, the voltage fluctuations are having less and less amplitude and finally settling on a new lower value. It could be that this behavior is caused by my setup not following the expected quick charge protocols. I was trying to find a spec of the protocols, but it appears that the whole handshake and comms are already baked, ready to use into hardware chips, for example Snapdragon processors. My concern is that since I'm basically always commanding 12 volts, it may be that as the battery drains, the Xiaomi announces and starts a downgrade to 9 volts, which would probably be accepted by a phone or a tablet, but my dumb USB trigger device commands it right back to 12 volts. This repeats more and more until the Xiaomi decides that it just can't do it anymore and ignores the 12 volt command. Be that as it may, let's briefly look at the beginning of the plot where I ramped up the current. The red line is the plot of the current increasing from 0 to 1.2 amps, and the blue line shows the voltage dropping from just below 12.4 volts in idle to around 12.1 at full load. There's a small area where the load is below about 0.5 amps and the power bank seems to produce some fluctuations. But this high resolution plot really exaggerates the effect. The fluctuations are really very small, about 20 millivolts, and harmless. I tried the same setup with a USB trigger tester set to 9 volts. First, the recording of the current ramp up. For 9 volts, we go all the way to 2 amps, which is the specified full load setting for the Xiaomi at 9 volts. And then letting it run at 2 amps until it's completely discharged. The 9 volt 2 amp load graph is on the left here. You will notice that now we have two areas where large fluctuations occur, from 9 volts down to 7 and later from 7 volts down to 5. The spike at the end was caused when the load was disconnected. The 9 volt efficiency at 2 amps is just 66%, slightly worse than for 12 volts. For good measure, I repeated this test with 1.5 amp load, which is what my phone normally draws when it's fast charging, and in this case we are back to one area of fluctuation from 9 volts down to 7, which also occurs much later. So with just 75% of the maximum allowed load, the Xiaomi managed to avoid downgrading to 5 volts as it did before, and the efficiency has also improved to 70%. The current ramp up and the voltage response at the beginning of my 9 volt test looks perfectly normal. As I mentioned before, I suspected the problem of the fluctuations were caused by my USB trigger testing refusing to let the Xiaomi downgrade the voltage when the battery drains and the boost converter can't maintain the higher output voltage any longer. To test if this is the case, I decided to repeat the 9 volt test, but instead of my USB trigger tester and electronic load, I'm simply connecting my Samsung phone, which supports fast charging. I made sure the power bank was only about half full to increase the chances that it would want to revert to a lower voltage. This plot is shown on the top here. For comparison, I did the same test but replaced the Xiaomi power bank with a Motorola power adapter, so lack of charging capacity is no longer an issue. This is the lower plot here. The results are quite interesting. Firstly, in both cases the current is cycling periodically every 30 seconds between 1.5 amps and 0.7 amps, which is caused by the charge controller in the phone. Secondly, as expected, in the top graph, the Xiaomi shows increasingly fluctuations as it struggles to deliver 9 volts, but because the current cycles, this phase is drawn out because at each low current phase, the Xiaomi recovers back to 9 volts. Eventually, it can deliver 9 volts only at the low current phase, and so from there on, the voltage cycles in sync with the current between 9 volts and 7 volts. So in conclusion, my USB trigger tester wasn't the cause of the fluctuations. It is simply something the Xiaomi power bank does when its internal battery voltage falls too low. Last not least, a quick look at how the Xiaomi fast charges from a quick charge compliant Motorola power adapter rated at 5 volts 3 amps, 9 volts 2 amps or 12 volt 1.5 amps. To record this, I used the Bluetooth capability of the UM34C and the recording capability of the associated app. As you can see, the adapter and power bank agree to use 9 volts 2 amps, which is fine as it uses the maximum 18 watts possible in Quick Charge 2.0. A plot of the recorded data looks a bit unexpected. It appears that charging the Xiaomi is anything but straightforward. Looking at the red line, which is the current, we see many short gaps where the current drops to half or even to zero for a moment. Overall, the current ramps up to 2 amps, but then increasingly more frequent drops to just over 1 amp for extended periods. This could well be the result of thermal protection kicking in, either in the Xiaomi or the power adapter or both. It is also possible that the short pulses are Xiaomi's version of pulse charging. We saw a similar pattern when looking at charge current produced by the Huntsman battery charger in one of my earlier videos. A bit more worrying is the blue line showing the voltage. There are 2 or 3 short voltage spikes of up to 15 volts magnitude. He has a zoomed-in view of some of the spikes. I'm not sure if this was caused by the power bank or the power adapter, but it seems that neither mind too much. I only have one power adapter that supports the 9V 2A expected by the Xiaomi, so I can't try another adapter to see if it behaves differently. But what I can do is to take the same power adapter, use my USB trigger tester to set it to 9V, load it with 2A current and record the behavior with my power mod. The result is this graph here. As you can see, for the whole time I loaded it with 2A, which was almost 1 hour, the output is rock solid. The adapter got very hot in the process, but kept on going. So we can conclude that the fluctuations and the current reductions we have seen earlier are all caused by the Xiaomi and not the power adapter. In conclusion, there's no question that despite the strange behavior in some instances, the Xiaomi is the more capable power bank, and that at a far lower cost. But interestingly, specs are not everything when it comes to what people like. Given the choice, everyone I asked to choose one of the two for taking on a hike or even just a long journey went immediately for the Energizer, even when told that the other one had more capacity or could fast charging. The chunky rubberized exterior is much nicer to handle, and it gives confidence of throwing it into a backpack without much worries. The sleek metal housing of the Xiaomi, on the other hand, is rather slippery, scratches very easily, and it just doesn't look and feel like a device meant for the on-the-go usage. I hope you found that little comparison useful, and thanks for watching.